Good evening, Lamai. Okay, let's start the session for today. Right. Last day we had discussed about the Lewis structures, right? Lewis structures and how we Lewis structures and how we are draw the structures, right? With the starting session of the unit 2, right? So today let's discuss about the resonance structures. So our major topic here today is to discuss about the resonance. So when it comes to resonance, resonance structures, resonance hybrid, and how to use the resonance hybrid to come up with the bond lengths and bond strengths, those will be discussed, right? Okay, today our lesson is about the resonance structures, right? So first of all, let's draw some structures for the N2O molecule, the molecule N2O, and then quickly come up with the idea what this resonance means and what are these resonance structures, right? What this means, right? Okay, first with the knowledge of the last day we have gained, let's draw some structures for the N2O molecule. So I'll quickly go through the steps we had followed last day, right? Then let's come up with the N2O, right? So I'm going to draw the N2O molecule, right? Again, last day with the homework, I think question number 6 there in your tute, right? It was about N2O, the drawing Lewis structure of N2O, right? So let's do the working there and let's come up with the N2O Lewis structure, and then we can come up with a clear idea what this resonance means, right? Okay, so let's draw this stuff, right? So when it comes to N2O, let's do the electron count first, right? So with the electron count, right, we can come up like this, right? So with nitrogen, right, right, some 5 electrons will be given by one nitrogen, right? 5 into 2, right, as 2 nitrogens are appearing. So nitrogen is in your group 15, that is why 5 electrons are given to the valence electron count, and 2 of nitrogens are there. So with oxygens, right, oxygen as group 16 element, 6A element, one oxygen will give 6 electrons to the valence electron count. So all together you will have 10 electrons there, right? 10 electrons there. So if you are to come up with electron pairs, number of electron pairs, so 10 have to be divided by 2, that will give you 5 electron pairs, 5 pairs. So if you are to think of the N2O, the skeleton, N2O the skeleton, right? Let's draw the skeleton here, N2O the skeleton, right? So for the skeleton of N2O, right, 2 electron pairs are used for the skeleton, right? 2 used, right? Okay, that is with the skeleton, right? The N2O. So the remaining pairs, which are known as lone pairs, the lone pair count is going to be then 3, no? So N2O, right? So 10, sorry, it is 16, sorry for that, it is 16. So 8 pairs for the skeleton 2 is used, so lone pair count is going to be 6 pairs, right? So let's give those 6 electronic pairs to your skeleton, right? Let's give you those 6 electronic pairs to your skeleton, right? Okay, this is your skeleton, right? So when allocating electrons, when giving electron pairs to the skeleton, first you have to fulfill the octets of the cone atoms, right? So fulfilling octet means completing 4 pair situation with those second row non-metals, right? So 1 electronic pair is there with the oxygen, completing the 4 pairs means another 3 electronic pairs should be given. The octet is completed with this oxygen, so we have to complete the octet of all the cone atoms normally, right? So 6 electron pairs have been allocated now, right? Okay, so now we have a problem. What is the problem? The problem is with the center atom. after allocating the electron, we have to look at about the center atom. If it is a second row non-metal, definitely it should fulfill the octet. If it is a second row non-metals, our major concern is to fulfill the octet. If it was a third row above atom, then our major concern is to come up with the least charges on that atom. Anyway, this is second row non-metal, so we have to fulfill its octet. So actually, when we are trying to fulfill this guy's octet, we have three methods. The three methods are available. Three such methods are available to complete the octet for this nitrogen. The one method is by giving both the electronic pairs, the 4 pair situation should be completed with this nitrogen. So 2 pairs are already going around the nitrogen. So this nitrogen needs another 2 pairs. So both the pairs can be given by this nitrogen. That is one method of fulfilling the octet for the center nitrogen. So if so, we will come up with, right, a structure like this. If that is the electron movement to complete the octet of this nitrogen, you will come up with a structure like this, right. So your structures, sorry, I will draw it in red color, right. So for the red color movement, right, electronic movement, so your structure would looks like this, right. Okay, if you are doing the red colored electronic movement to complete the octet of this center nitrogen. So if you allocate the charges on these atoms, so 1, 2, 3, 4, 5 electrons are going around nitrogen. This should have 5. You have 5 electrons are going around, so no charge. So this nitrogen should have 5 electrons, but now the number of electrons going around that nitrogen is 1, 2, 3, 4. 5 should be there. Only 4 are going there. So 5 minus 4 is plus 1. So with this oxygen, there should be 6 electrons to go around the oxygen for a neutral oxygen, but now you have allocated 1, 2, 3, 4, 5, 6, 7. 6 should be there. Now you have allocated 7. That means minus 1 is a charge of that oxygen. So this is the structure you will get if you fulfill this nitrogen's octet like this. So one can fulfill this guy's octet by donating only one pair from this nitrogen, and from the other pair can be donated by this oxygen, right. There is another way of fulfilling the octet of this nitrogen. So if you have done like that, so you will come up with a structure like this. So already one pair was there and another pair was given in between 2 nitrogens, right. So already one pair has been there and another pair was given by the oxygen. So 2 bonds are there between the nitrogen and oxygen. So 2 pairs are remaining like this. For this one also 2 pairs are remaining. Then let's put the charges on these atoms, right. So if you put the charges on this atom, 1, 2, 3, 4, 5, 6, 5 should be there, 6 are going there. So 1 electron is in excess, so minus charge. There should be 5, but 1, 2, 3, 4, only 4 are allocated. So the charge is plus 1, lack of an electron. There should be 6 here around the oxygen. Now you are with 1, 2, 3, 4, 5, 6. 6 here and 6 are there. So the oxygen carrying no charge there, right. So and one can think of, right, kind of electron donation, right, like this to fulfill the octet. Both the electron pairs to be donated by the oxygens. Another method of fulfilling the octet, the third method. If you are to do so, right, you will come up with a structure like this. These are 3 available methods to complete the octet of the central nitrogen. So if you have to allocate the charges would look like this, right. Charges would look like this 2 minus here, right, 2 minus here, because nitrogen should have 5 electrons for a neutral nitrogen, but now you have 1, 2, 3, 4, 5, 6, 7. You have allocated 7 electrons. 5 minus 7 is minus 2. That is how the minus 2 charge obtained by the nitrogen. So these are 3 acceptable Lewis structures. One can draw for the same N2O molecule, for the same N2O or the same skeleton. Now we have already written 3 acceptable Lewis structures. Actually these things, if you can draw more than one acceptable Lewis structure for a given skeleton, then we refer them as resonance structures. Resonance structures. So that is the definition. What are resonance structures? Resonance structures are the Lewis structures if we are able to draw more than one acceptable Lewis structure for a given given skeleton, right? For a given skeleton, for a given atomic skeleton, for given molecule, if you can draw more than one acceptable Lewis structures, then those are referred to as resonance structures. So these are considered as resonance structures, right? These are the resonance structures. Resonance structures. Normally we denote these resonance structures with this symbol, this double headed arrows. With this symbol, normally we denote the resonance structures, right? So if this kind of a thing was appearing, A and B with this symbol, this says A and B are resonance structures. A and B are resonance structures. That means A and B carry the same atomic skeleton. A and B carry the same atomic skeleton. A and B are with the same net charge. The net charge of these molecules are equal to the charge here, the 0. So A and B, if you look at a situation like this, so A and B are resonance structures because of this sign. That means these guys are with the same atomic skeleton. These guys are with the same net charge, right? So that idea should be known with this symbol. This is the symbol which indicates that the constituent species are resonance structures related by the resonance, right? Okay, these are the resonance structures. So you got the clear idea what this resonance means, right? These are the resonance structures one can draw for the N2O molecule, right? Okay, so you got the idea now. That is about the resonance structures, right? Right, our first consideration is done. Resonance structures, right? Okay, now let's discuss about how to comment on stabilities of these resonance structures. That is our second consideration for today. Now we had some, we are with good idea what this resonance means, what these resonance structures are, right? Now let's concern about how to comment on the stabilities of these resonance structures, right? So we are with three acceptable Lewis structures which can be drawn for the same N2O molecule, right? So let's discuss about commenting on the stability of these ones, right? Okay, now next consideration is commenting on the stability, right? So stability comments, it's done. Second thing is about, right, comment on stability. That is what now we are doing, commenting on the stability, right? Okay, stability concerns, right? Okay, so how to comment on stability, right? So there are structures, there are acceptable Lewis structures which are concerned as stable structures as well as unstable structures, and some are concerned as less stable structures. So we should be able to correctly label whether these structures are stable, unstable or less stable. Those are the three labels we use in A levels, right, to comment on their stabilities: stable, less stable and unstable. Let's discuss about the stability rules. What are the rules we can apply, right, to concern about the stabilities of these structures, right? Okay, few rules are there. Before that, let's consider about what this stable means. Before going for those rules, right, stability rules, let's discuss a bit about what this term stable means. Stable, yes. So stable means like this. It's kind of a thing like this. Stable means if you are not changing if something is not changing for a longer period of time. If something is not changing for a longer period of time, right? If something is stand for a longer period of time without a change, then we can say such a thing is stable. Such a thing is stable, right? So stability is that if you are not changing for a longer period of time, right, you are stable. So sometimes we say that guy is very stable, his words are very stable, right? He is saying again and again the same thing. He is not changing throughout the years. He is saying the same thing. He is stable. His words are stable, like that. So if something is not changing for a long period of time, we can consider it as stable. If something is changing, if something is to change in no time, with a quick time interval, if something changes their conformation, if some bonds are to be broken, if some electrons are to be transferred with the atoms, the structure changes with no time, then we consider such structures as unstable or less stable, right? Okay, that is the meaning of stability, right? So actually, for not changing for a longer period of time, not to change for a longer period of time, basically your interactions should be less. Your interaction should be less. If you are interacting heavily, with the other particles and the stuff, then you will change eventually, right? As we are interacting with the others, right? So we are changing, our ideas are changing. As we are talking with the others, their ideas are also coming towards us, towards our brain, and so we are trying to think of those ideas as well, so we will change them. If you are not talking with others, if you are not interacting with others, then we won't change, right? So to become stable, to be as stable, not changing for a longer period of time, it is better to have less interactions. More the interactions with you, that means your stability decreases. That is the idea, no? Right? Okay. So what will happen? So the case is this. So if you are with charges, that is what happens, right? Let's say you have a structure like this, right? And the structure is with charges. Some positive charges, right? Structure is with charges. Okay, then what will happen? If your structure is with charges, right, towards that structure, the negative charges will attract. If you are with a plus charge in your structure, the negative charges is attracted, right? If you are without charges, no particles will attract towards you. If you are with charges, the opposite charge particles will attract towards you. They will interact with you. That is why we are saying a structure with charges are with less stability. If you can draw a structure without any charge, on atoms, then that would be the best structure. Because no interactions will occur with the outsides. So that you can stay for a longer period of time without a change, because with no as you are not dealing with any interactions, right? When you are with charges, your structure becomes unstable. So basically, right, bearing a +1 charge, -1 charge is okay actually. Bearing a +1 charge, -1 charge is okay. But if you are with +2 charge, +3 charge, what will happen? +2 charge, +3 charge means, right, not the particles which are nearby, but also the particles far away from you. The opposite charge particles far away from you also feel the charge of you, so that even those particles will attract towards you. So bearing a heavy charge, more than 1 unit of charge, will decrease your stability heavily. So bearing a +1 charge, -1 charge is okay. For sometimes, for some molecules, we can't draw any structure without charges, lamai. So this molecule even we can't draw any structure, any acceptable structure fulfilling the octets. We can't draw any acceptable structure without charges, right? So for those instances, bearing +1 -1 charge is okay, but if you are bearing some greater charge, greater magnitude of charge, that means more than 1 unit of charge, +2, +3, -2, -3, if you are bearing that kind of a larger magnitude of charge, then this is what happens. Not only the particles which are close to you, but also the particles which are far away from you also attract towards you, right? So that your interaction amount will become very large, so that your stability will be very less then. So the structure becomes less stable, when you are carrying a charge with more than 1 unit. Those are the ideas, right? That is how the structures become unstable, less stable, right? Okay, those are the main reasons, right? Okay, so let's again discuss one by one, point by point, clearly how to comment on this stability. Now I think you have got some clear idea about what stability means. Let's discuss one by one the points what we should concern to comment on these stabilities of these structures, right? Okay, so these are the points, right? Let's come up with the points now, right? As you know the reasons now, no? Right? These are the major points. So you have to follow the points one by one. Right? To check the stability of the structure. The first concern, right? The first concern is, if you can draw a structure without charges on any one of the atoms. If you can draw a structure without charges on any one of the atoms, that structure is the most stable structure you can draw. Because no interactions with the others. So you can stand for a longer period of time without a change, right? Okay, but here you clearly see such a structure is not there. So we can't say, right? We can't comment by looking at that point whether the structures are stable or not, because all the structures are carrying some charges. So that point we can't think of for these three resonance structures, right? The first point is what? If you can draw a structure without charges on any of atoms, then that is the most stable structure. The best acceptable structure. For this example, such a structure is not there, right? So we are not going to concern about that thing, right? So this point is not valid with the resonance structures of N2O. Then we have to consider the next points, other reasonings. The reason number one. The first two reasons are about some these reasons are about taking your structure into a unstable nature, right? The reasons. First reason, if a positive charge appears on most electronegative atom of the system, then the structure is considered as a unstable structure. Structure is considered as an unstable structure. So if this thing is there, so we consider the structure as an unstable one, right? Why is that? Always ask why is that. The reason is electronegative atoms are the ones which are more keen of electrons. So bearing a positive charge on that means that guy is lack of electrons. That guy is lack of electrons. That can't be for a long, no, Lamai. That can't be for a long, no. That can't be for a long, right? Because that is the one most keen of electrons, right? So that then what will happen? That guy will grab some electrons from one of the atoms, from the nearby atoms. That most electronic atom will grab some electrons towards itself, so that the structure will change eventually. With no time, the structure will change. That is why we say you can't have a stable structure with a positive charge on most electronic atom, because that guy will grab some electrons from the nearby atoms and the structure will change. So those structures are highly unstable, eventually quickly change. That is what means by unstable, right? So we have such structures here. See, this one is unstable, this one is unstable. See, the most electronic atom of this compound is oxygen. Nitrogen is with 3.0 electronity, oxygen is with 3.5, the most electronity is oxygen, but it is bearing a positive charge. So that is unstable. So this structure is unstable. So you can comment this structure as unstable. The other structures are not with such a problem. This is unstable. What is the reason? You can write the reason. Reason is positive charge on most electronegative oxygen atom. That is the reason. That is the reason to become unstable. We have another reason. Two reasons are there for structure to consider as unstable, right? The second reason is adjacently connected atoms are with same signed charges. That is the second reason. Structure to become unstable. That is another reason. What is happening when this thing happens? When adjacently connected atoms are with same sign charges, the repulsions will occur. If the two atoms are with same sign charges, what will happen? The repulsions will occur. Ultimately, it will break the bond. It will change the structure. Unstable. Structure will change in no time. Unstable. Right? So even with the negative charges, if the adjacent connected atoms are with same sign charges, repulsions will occur and bonds will break. Structure become unstable. So that thing happens with this structure. These two atoms are adjacently connected atoms with same sign charges. So this is unstable due to that also. Two reasons for this structure to become unstable, right? So we can write the second reason: adjacently connected atoms are with similar signed charges. Those are the reasons for a structure to become unstable, right? No, structure to become unstable. Okay, so these guys are not coming with those reasons. So these are not unstable structures. Okay, so stability reasons should be considered in order, right? In order. First we consider these two things, right? If these 2 points are not appearing with your structures, then those are not unstable. These two are not unstable. We can't come in these two as unstable. Then we are coming up with the third point. So third point is about less stable. So if you are with the third point, such a structure is referred to as less stable, right? These are less stable point. So these two things should be considered orderly, right? In order. Third point is, if you are with a more than 1 unit of charge, on a considering atom, that is referred to as high charge density on considering atom, on, let's say, atom mix, any kind of atom. So high charge density, this comment will be written when you are with a more than 1 unit of charge, that means -2, -3, +2, +3 kind of a charge on atom. So here also we can see that more than 1 unit of charge, but we can't comment this as less stable because we are coming with the order. This structure is considered as unstable. Right? So we can't comment it as less stable. It is unstable already, right? Okay. We have to consider the points in order, right? The fourth point is about high charge dispersion. That is the fourth comment. High charge dispersion or high charge distribution. So this comment is written when you have atoms, you have more atoms with charges compared to the more stable structure. This comment can be written only when you have more atoms with charges compared to the more stable structure. First of all, there should be a more stable structure, right? Compared to that, if you are with more atoms with charges, then only you can write this comment. This is a comment for consider the structure as a less stable one. And keep it in mind, to comment on this, before that you should identify the most stable structure. Right? Relative to that, if you are with more atoms with charges, then only you can come up with this comment. Right? Okay. There is another comment, right? Which leads for your structure to become less stable, right? Okay. So for these two atoms, for these two structures, those 2 points are not valid. Not valid, because out of these two, one of the thing should be the more stable structure. So compared to that, the other one is not carrying more charges, more atoms with charges. So that fourth point is not valid for these two as well. These are the only 3 resonance structures possible, right? Okay. Fifth point. So actually, Lamai, if these 4 points are not there with your structure, if the concerned discussed 4 points are not there with your structure, then we comment those structures as stable. If the 2 reasons to become unstable is not there, if the 2 reasons to become less stable is not there, then your structure is stable. If it is not unstable, if it is not less stable, then it is stable. No? It is stable. No? So these 2 structures are considered as stable. So you have to concern these comments in order, right? Right. So these 2 structures are considered as stable, right? Okay. Then few more stuff for structure to become more stable. Few more stuff to consider for structure to become more stable than the other. So to consider which is the best structure, which is the most stable structure, we can concern about few more reasons, right? The 5th and 6th points. Actually, those points are appearing with these structures, right? What are those points? 1 point, right? If your structure is with a negative charge, on the most electronegative oxygen atom, or with the most electronegative atom, most probably it is the oxygen. If your structure is with a negative charge on the most electronegative atom, then such a structure is considered as a stable structure, and it will attain a greater stability by that point, right? So here such a structure is there. See, so we can say this guy is more stable as you are with a negative charge on more serotonin oxygen. More serotonin atom oxygen, right? So that is one reason for become more stable. The other reason to become more stable is adjacently connected atoms are with opposite sign charges. The two reasons are the opposite of these two. Right? Adjacently connected atoms bearing opposite sign charges. Then what will happen? These two will attract heavily. That will confirm this bond. Confirm this bond means bond is not going to break. That means this structure can exist for a longer period of time without a change, because the bonds are not breaking, right? So bonds will strengthening by the attractions of these two atoms, as those are bearing opposite sign charges. So that is a good reason to become more stable, right? So adjacently connected atoms are with opposite charges. Adjacently connected atoms are with opposite charges, right? So even this structure carrying that point, right? These two guys are with opposite charges. Are with opposite charges, right? So that is how we are supposed to comment on the stability, right? So we can draw three resonance structures for the N2O. Right? Those resonances are indicated by this sign, right? And they are with non-equal stabilities. The stabilities differ. This one is unstable, this is stable, and this is the most stable structure, and we have discussed the reasons to consider them as stable, unstable, and less stable, right? So that is the first discussion for today, right? So resonance structures are the ones, resonance structures are actually the structures we can draw, the acceptable Lewis structures we can draw for the same skeleton, right? If you can draw more than one acceptable Lewis structure for the same skeleton, those are referred to as resonance structures, right? So those could be with unequal stabilities, right? So this is a good example for that, resonance structures, right? So we'll draw a few more resonance structures now, right? And let's try to comment on their stabilities as well, right? Let's draw a few more, right? So with your next example also, SCN minus, another good example. Let's draw some resonance structures for SCN minus as well, right? SCN minus as well, right? Let's quickly draw for the SCN minus as well the resonance structures possible, right? The SCN minus. Quickly come up with the electron count as well, right? Your central atom is carbon. Central atom is carbon, it is the least electron atom, right? 2.5, sulfur is 2.6, right? The carbon is the central atom, right? So the carbon, right? So first do the electron count and SCN minus, right? SCN minus, central atom carbon. First do the electron count, right? Sulfur carrying 6 electrons, sharing 6 electrons to the valence count. Carbon sharing 4 electrons, group 14. Nitrogen sharing 5 electrons. So altogether you are with one more electron in excess, minus 1 charge. So altogether you are with 12, 16 electrons. So electron pairs 16 divided by 2, that is 8 pairs. Then how many allocated for the skeleton? For the skeleton, 2 pairs are allocated. So you are remaining with how many pairs? 6 pairs. Right? So allocating those pairs to these cone atoms. First to the most solitary atom, completing the octet of that thing, means completing the 4 pair situation for that. Then you can complete the octet for the other cone atom. 6 are gone. Now this carbon is not fulfilling the octet. We have problem. So we have to donate 2 electronic pairs towards this carbon. 2 electronic pairs towards this carbon. Right? Because 4 pairs should be there around the carbon, as it is a second non-metal. Right? So those 2 pairs can be donated both by this sulfur, then you will come up with this structure, right, this structure. So you can mark the charges 1, 2, 3, 4, 5, 6 should be the only 5 is there, so plus 1 charge, right. So 1, 2, 3, 7, 1, 2, 3, 4, 5, only 5 should be there for nitrogen, so minus 2 charge. Carbon is without a charge, 4 should be there and 4 is there. Oh, one can donate the pair, both the pair from the nitrogen, so that you will come up with this kind of a structure. Between carbon and nitrogen, 3 shared pairs are there with the donation of 2 pairs towards the center. So this is the structure. With this structure, if you allocate the right charges, this will come up with a minus charge, because only 6 electrons should be around sulfur, as it is group 16 oxygen's group, but now we have allocated 1, 2, 3, 4, 5, 6, 7. That is a Cn minus, another resonance structure, and one can donate 1 pair each from sulfur and nitrogen towards the center, so that you will come up with this kind of structure. No? So when you have to allocate charges, you will have a minus charge here, that the charges are without charge. So these are the 3 resonance structures possible for the Cn minus. 3 different structures, 3 different acceptable structures which can be drawn for the given skeleton, for the given molecule or the given ion. The resonance structures, right? These are the resonance structures possible for Cn minus. So let's comment on their abilities. Right? Okay. So first reasoning. What are the first reason? Reasons to become unstable. What are those? Positive charge on the most solitary atom. Adjacently connected atoms are with same sign charges. Do we see any one of those things appearing with these? Positive charge on the most solitary atom? No, the most solitary atom of this system is nitrogen. Nitrogen is not bearing any positive charges with any of the structures. So that point is gone, not there. The second point, adjacently connected atoms are with same sign charges. No, it is also not there. So neither of these structures are unstable. No worries with that. Right. Second considerations, the third and fourth points. Those are considerations about less stable situation. Right. High charge dispersion and high charge density. First, let's consider about the high charge density situation. If one of your atom carrying more than 1 unit of charge, then that is referred to as a high charge density situation. -2, -3, +2, +3 situations. Yes, we see such a charge appearing here, this nitrogen. So this is a situation with high charge density. So this structure is less stable, less stable, less stable. What is the reason? High charge density on nitrogen. High charge density on nitrogen. If you are with more than 1 unit of charge on one of your atoms, that is high charge density situation. That is a reason to become less stable. This is less stable. What is the other reason? What is the other reason to become less stable? High charge dispersion. High charge dispersion. Yes, that is also appearing with this structure. High charge dispersion. What is that? High charge dispersion means when you have more atoms with charges, when you have more atoms with charges compared to the most stable structure you can draw, compared to the most stable structure you can draw, if you are with more atoms with charges, then those are referred to as high charge dispersion situation. So here we see that one of these things should be the most stable structure, no? One of these two things should be the most stable structure, right? So that this structure is with two atoms with charges. Compared to these things, it is a high value. Compared to these structures, only one atom with charges, two atoms with charges is a higher number. So more atoms are with charges compared to the most stable structure. One of these should be the most stable. So it is a reason to become unstable, less stable. So another reason for to become less stable is more atoms with charges. This is written as high charge dispersion or high charge distribution, right? More atoms with charges. High charge dispersion or distribution. Right? So that structure is less stable. Less concerned about these two. The next reason. So reasons to become less stable is also not applicable with these two structures. High charge dispersion situation, no. High charge density situation, those two situations are not there with these two structures. Let's consider the next reason. So these guys are, first of all, we can refer these guys as stable, first of all, right? Because if the reasons to become unstable or stable not appearing, then those structures are stable, na? Those structures are stable. Reasons to become unstable or less stable not appearing with these two structures, those are stable. So now we are going to discuss, now we are going to select which is the most stable, which is the most stable. If you have more reasons to become more stable, then that will be the most stable structure, right? Okay. So to become more stable, what are the reasons available? Yes, one thing is adjacently connected atoms are with opposite sign charges, but here such thing is not appearing. The second reasoning is, right, most electronegative atom of the system bearing a negative charge. So here with this system, what is the most electronegative atom? That is the nitrogen. Nitrogen with its 3.0, this is 2.5 and this is 2.6, right? Nitrogen is the most electronegative atom, that guy bearing a negative charge. That means that is a reason to become more stable, right? This is the more stable. The reason is what? Most electronegative. Atom. Nitrogen in the system is nitrogen. In the system, this nitrogen bearing a negative charge or negative charge on the most electronegative atom of the system. Negative charge on the most electronegative atom of the system, right? So that is the most stable structure. So that is how we are supposed to comment on these structures, right? Okay, right. That is all about resonance structures, right? That is all about drawing the resonance structures, right? And commenting on their stabilities. Actually here we have discussed about I have discussed about two examples. With both the examples I have concerned some asymmetric skeletons. Some asymmetric skeletons have been discussed, right? So we will discuss a symmetric skeleton as well. We will discuss a symmetric skeleton as well. That is better to consider such a skeleton as well to when going towards the next topic, which is actually known as the resonance hybrid. Okay, right. So these are some resonance structures. Okay, so let's go. If you are to look at your note, right, in your note, right, so at the page number, which one? At the page number 9. At the page number 9, these structures are there, resonance structures, that note is there. You can go to that. The resonance structures note is there at the page number 9, right? And at the page number 6, no? At the page number 6, those stability concerns, the reasons are there. So go to that as well. Those are the things we have discussed now. Right, just completed, right? So stability reasons are there at the page number 6. You can draw these things at the page number 6. Even this one, even the earlier case, right? With the N2O. So that resonance structures note is there at the page number 9. Just go to that and do the homework as well. So few molecules are there to draw the resonance structures, right? So few molecules are given. So if you need, I will draw few one or two again, another one. Right? I can draw another resonance structure for you before going to resonance hybrid. Right? Do your homework, Lama. Do your homework at home. Right? So at the page number 9, few molecules are there for you to draw the resonance structures. Right? Okay, do that. I'll do one of those again, right, for you to come up with good knowledge, right? So I'll draw the resonance structures for HCO3 minus, right? Okay, let's draw for HCO3 minus as well, right? HCO3 minus, which is appearing in the page number 9, right? This is completed, so you can take a screen capture if you need. The 9 people, right? Yes, online girls, do you have any questions? If you have any questions, just use the chat box, or you can ask by the mic as well, right? Or you can raise your hands, right, so that I can hear, right? Okay. Let's quickly do the next stuff. I'll draw another one of those, right, to quickly gain some more knowledge, right? So let's draw the resonance structures for carbonate before going for the resonance hybrid things, right? Let's draw the resonance structures for carbonate. So HCO3 minus. HCO3 minus. HCO3 minus. So it is an asymmetric molecule. Another asymmetric one, no? Yeah. HCO3 minus. So HCO3 minus. First do the electron count. With the hydrogen you get 1 electron. With the carbon you get 4 electrons as group 14. With 3 oxygens, 1 oxygen gives 6 electrons each into 3, as 3 oxygens are there, and minus 1 charge is there, so another electron is added. That is what minus 1 is says, right? You have one more electron than the electrons in HC and 3 O's, right? So the summation is 18, 19, 20 and 24. 24 altogether electrons. So electron pairs 24 divided by 2 is 12 pairs. Then for the skeleton, the HCO3 minus skeleton, right? HCO3 is minus skeleton. Skeleton is this. Skeleton is this. So for that skeleton, 1, 2, 3, 4. 4 pairs have been used. So the remaining is 8 pairs. Remaining is 8 pairs, which are known as lone pairs to allocate. Eight pairs. Okay. Let's assign these 8 pairs. Right? 8 pairs. First allocate the pairs to the cone atoms, fulfilling the octets. Octet means 4 pair situation should be fulfilled. So 1 pair is there, 2, 3, 4. 4 pairs completed for this oxygen. 1 is there with the oxygen. 2, 3, 4. 4 pairs are completed with this oxygen as well. So when then comes to this hydrogen. So hydrogen is not supposed to fulfill the octet. Hydrogen is group first row element. So only 2 electrons are allowed with the hydrogen's valence shell. That is completed now with the bond. 2 electrons are there. So hydrogen is not concerned to give the electrons. So next atom. Ultimately we come to the center, right? If this is not there, then for this one we need we have another 2 electron pairs left, right? We have with 2 electron pairs, so we can give those to this atom, right? So that is that guy's octet is also fulfilled, as 4 electron pairs are going around that oxygen. 1, 2, 3, 4. 4 electron pairs means octet, 8 electrons, right? Okay. After allocating the 8 electronic pairs, now we have to concern about this center atom. Yes, it's a second row non-metal. So octet should be fulfilled with that atom as well. So 4 pairs should be fulfilled with this carbon as well. So only 3 pairs are going around still. So 4th pair can be donated by this oxygen. 4th pair can be donated by that oxygen. So if you are to do so, right, you will come up with this structure. You will come up with this structure. Right. So if you have to put the charges, this will carry some minus charge. Right. So one can donate the 4th electronic pair towards the carbon like this, so that you will come up with this structure. Right, this structure. Then you can allocate the charges on these atoms, right? So for oxygens you should have 6 electrons, but this oxygen this oxygen is with 1, 2, 3, 4, 5, 6, 7. 6 should be there and 7 is there. So 6 minus 7 is minus 1. And these are carrying 6 electrons each with this oxygen, so no charges there. 6 should be there and 6 are allocated. Carbon is also without a charge, right? So these are 2 resonance structures. These are the 2 resonance structures we can draw for the HCO3 minus, and these are referred to as resonance structures with equal stability. These are referred to as resonance structures with equal stability, right? These are referred to as resonance structures with equal stability. Both are stable. Both are stable, right? Both are stable. So one can see these are resonance structures. Resonance structures with equal stability. Resonance structures with equal stability, right? So both are considered as stable structures. Negative charge is on the most oxygen as well. No reasons to become unstable or stable. Yeah. So such resonance structures can be drawn for HCO3 minus, right? So such kind of situations are also there, right? Sometimes the resonance structures may have equal stability, because such things will appear when with the symmetric skeletons. With the symmetric skeletons, such things will appear, right? This skeleton is symmetric, yeah, kind of symmetric skeleton. So that is what we expect, right? So that is all about the resonance structures.